Okay, so this is a rather ambitious title. It's really going to be part tutorial and part progress report. This, but but uh, but so I'm going to talk about some recent results and a little bit about how to um, how to how to do what the title suggests. So photoionization, I don't think has been talked about yet in this conference in any detail, but it's likely to be important whenever you have a strong source of X-rays or ionizing radiation and gas nearby, which absorbs and reprocesses the X-rays and makes spectra that we see. And we've gotten some beautiful spectra from the Chandra HETG and XMM gratings as well. And we hope to have some more beautiful spectra from CRISM in the future, not too distant future. So, sorry. So photoionization modeling is simple. In a sense, it's very much like collisional plasma modeling. We have statistical equilibrium, which determine the level populations of the constituent atoms and ions in the gas, and you need to calculate that, and then you need to calculate the emission or absorption that's associated with those level populations. The difference, one difference is that that you need to also calculate the temperature, or at least it's customary to calculate the temperature using a radiative equilibrium assumption. So that removes the temperature as a free parameter from the calculation. However, but there still is an important free parameter, and that's the ionization parameter. Turns out to be the ratio of the ionizing flux to the gas density. And then also, obviously, one needs to include the effects of the photoionization and the photoexcitation from the source of radiation, which is responsible for ionizing and exciting the gas. So, and so we also always customarily assume equilibrium for the level population, so you neglect time dependence, and then you can calculate everything. So a slight progress report on what's new in the XStar code, which can be used to calculate all these things. We've recently updated the atomic data with new R matrix calculations of K-shell processes in all the elements with atomic number less than 30, which had been previously treated in a very approximate way using hydrogenic scaling. So these are all the odd Z elements above oxygen, plus all the iron peak elements other than iron and nickel, which had also previously been treated. So this basically results in a doubling of the volume of atomic data in the XStar atomic database, and hopefully these things will be useful for future observations with future instruments like CRISM and Athena. And then in addition to that, we've implemented processes which are important when the gas density is very high, and this is likely to be important in X-ray heated accretion disks very close to black holes, particularly in galactic black hole systems, where the densities can be almost up to solid densities, at least nominally. So we now think we have better treatment of the level population, the continuum lowering, and the density dependent effects up to densities approaching 10 to the 22 per cubic centimeter. And then finally, we are trying to get into the 21st century, and we have some Python tools for parsing the output, and this is an ongoing process. So now I'd like to just give you a little cookbook as to how you might, how one should construct a photoionization model to fit to a spectrum that you might obtain with HETG or a future instrument. And so let's just say you have some data, and this is a kind of a flow chart which takes you through the kind of decisions you would have to make in order to get to the point where you have a model which might be physically realistic. And so obviously, in order to proceed, one needs to understand what the spectral energy distribution is, the global spectral energy distribution is, and that's useful. That's needed for modeling the photoionized spectrum. And then the second step is to understand what lines are in your spectrum. So I'm not going to give you an example, but obviously if you have the iron K alpha line, that gives you a different result than if you have the hydrogenic iron line. And so you can sort of infer a ballpark ionization balance by looking at a spectrum. So you can have high ionization if the lines are, if heavy elements are highly ionized, or medium, such as the spectra that Victoria was showing a minute ago, or even a fairly low ionization situation where you just have neutral lines, which will still give you, should still give you interesting spectrum. So then you need to construct a model, a photoionized model, and that involves choosing the three main parameters, the ionization parameter, the gas density, and the column density, or something to do with the size of the region. You can reorder these in various different ways. And then you need to use a model to calculate, a code to calculate a model, which you can use inside of XSpec or specs to fit to the data. And so with XStar, you could use a table model, or the analytic version of XStar, which is WarMabs, or specs can do this for you as well. And then you look at the model and you look at the data, and you iterate around a bunch of different questions. You know, are you making strong enough lines? If you're not, then you need more column density or more gas in your model. So you increase that. If the lines are strong enough but they're not in the right place, then you need to change the conditions to increase or decrease the ionization balance in the gas by changing the ionization parameter. And then finally, do you get the right line ratios, like the helium-like, R and G ratios? And if you don't, then you can change the density or the abundances, or something to do with the microphysics of excitation, and iterate again. And finally, if you have a good fit, or a fit that looks reasonably good, then you still have some questions that you need to answer, which can sort of tell you whether you've gotten something that's reasonable. So final sanity check. And here are some of the things that you might include in your sanity check. I mean, first and foremost, there is a consistency, internal consistency that needs to be satisfied between these three fundamental parameters: the ionization parameter, the density, and the column density. And that really is, the column density has to be less than this quantity, the square root of the product of the luminosity, the density, and the ionization, divided by the ionization parameter. And you can see how this works, in the sense that you can't fit more gas into a certain volume than you have the size. The size parameter would allow you to do. And then you ask yourself, what's the emission measure? Is that plausible? Because you might be needing amounts of gas which are unphysical, but that depends a lot on the the source that you're interested in and some insight as to what's going on the source. And then the element abundances, if you require super solar abundances for everything, then that's a hint that you have something that might not be quite right. And then there are all kinds of more subtle questions, such as, are you resolving the lines? If you get a temperature from the RRCs, the radiative recombination continua, does that make sense with respect to the photoionization model that you're using? So, whoops, sorry. So is that, that's a question, may not be a fatal question, but certainly is interesting. Do you have multiple components of gas? Do you have multiple pieces of your photoionization model that need to be added together? And are you adding, are there many of them? Can you simplify that? And then you might want to look outside the energy band. Does this model predict things that you don't see in the hard X-rays or the optical UV? And finally, you should look at count space spectra. I mean, this seems obvious for spectral fitting, but it is sometimes neglected that count space is more revealing of what fits and what doesn't fit than looking in flux space. So now a couple of other things, a couple of other important physical things which I think get ignored sometimes. And that one of those has to do with the line width. And that is, if you look at the line widths that we expect physically from most lines are very small. So the thermal Doppler width or the natural width, or even the turbulent width, if the turbulent speed is comparable to the thermal speed, they're all, small, they're all a part in 10 to the 5th or a part in 10 to the 6th. Whereas our instruments have resolutions, of 1,000 at best. And so if you're fitting absorption spectra, even the very best absorption spectra that we've obtained with HETG, you're fitting very, very narrow, what are likely to be intrinsically very narrow features to unresolved features in your data. And this is a problem both from 3 different points of view. First, the sort of spectral fitting point of view. In other words, does your fit really mean anything? And then there's the computational point of view. Does your code actually calculate these things properly? Or does it just calculate e to the minus tau at the line center and put that in the bin where the counts are? I mean, really what one should do is to subdivide each bin into a very fine grid where you actually resolve these widths and then calculate an equivalent width based on that, which then you can put into your model fitting bin. And then the third thing is really the instrument itself. Do we really, is the instrument properly calibrated at, in the depths, in the centers of these lines? So are we actually, if the line were black, would we actually see that? And so these are all important questions which are hard to deal with, but worth keeping in mind when you're fitting to this kind of data. So then the next thing has to do with geometry. And in photoionization, you have, you're trying to fit something which is not really, it's not just a blob of hot gas. You actually have some structure. You have and we idealize these models as a sphere of gas with a point source at the center, and then the radiation propagates out, gets reprocessed, and turns into things that we see. And if we see gas along our line of sight, it looks like absorption. If we see gas away from our line of sight, it looks like emission. But the standard assumption is that the source is the gas cloud is spherical with the source at the center. And if you think about it, for pure scattering, and a stationary cloud of gas, these things should cancel each other identically, and you should see nothing. There should be a identical cancellation of the emission and the absorption. And this is kind of the classical treatment of the way these models were made back in the 1980s and 70s, so that scattering, pure scattering, could be ignored when calculating this stuff. Well, obviously, first of all, you can turn it into a thin shell. It doesn't change the answer qualitatively, but you can then say, well, maybe the shell doesn't really cover the source. And if that's the case, then you lose this cancellation, and you should see net emission if the source is, if you're not viewing the source, not viewing the gas along the line of sight to the source, or you should see pure absorption if you're viewing the gas along the line of sight to the source. And so this matters in terms of the spectrum that you see. And we treat this at least in the X-star code, we treat this using a covering fraction. So basically, this top panel corresponds to the traditional picture in which there really is no pure scattering included in the calculation, and all you see is a pure recombination spectrum. So I'll draw your attention to the helium-like lines at 570 EV, and you can see that these lines are in a ratio which is characteristic of recombination, in which the triplet and intercombination and forbidden lines are brighter than the resonance line. But if you include scattering, then the situation is reversed, and the resonance line becomes stronger than the other two lines. And there are quite a few papers in the literature, actually, where people have seen this ratio and they say, oh, well, it must be coronal gas, but it really doesn't have to be coronal gas. It can be resonance excitation, can be scattered. And so X-star treats this with the covering fraction. So if you set the covering fraction equal to 1, this corresponds to the traditional picture. And if you let it be less than 1, you include scattering to the extent that, some fraction of it, to the point where if covering fraction is 0, then it's pure scattering. And this makes quite a significant difference, as you can see in these spectra. So another thing that I'd like to point out is the fact that in photoionization modeling, the results depend a lot on the radiation field outside of the traditional energy band where photoionization is important. In other words, hydrogen has an ionization potential of 13.6 eV, and we sort of tend to think that only the radiation between that energy and up to a few keV, maybe 10 keV at the most, are important in what we see. But in fact, the two processes which are important for heating and cooling are free and Compton, and these things depend on the radiation field at all energies. And so what this means, these are expressions for the rates of these processes, and you can see that free is very sensitive to the soft end of the spectrum, and Compton it can be either sensitive to the soft or the hard end of the spectrum, depending on the shape, and that they can both win over photoionization heating if the ionization parameter is small. If the ionization balance is small, if the ion fractions are small. So if you really have to be careful when you look at this, and so for example, at high density, the free heating becomes important and changes the shape of these thermal instability curves in a qualitative way. And this is something that that requires not just a careful thinking of treatment of the physics, but also thinking about what is the very soft end of the spectrum of this spectrum. How far down into the IR can we extrapolate the spectra? How much of what we see is reprocessed in a distant region where it's not actually responsible for illuminating the gas that we're interested in, but we see it anyway, so we're fooled into thinking that it's important. these are all questions that are sometimes neglected in modeling these, in photoionization modeling.
Tim, you're
Okay.
at 20 minutes, so you have 5 minutes left.
Yes.
It looks like you're almost done.
Here's my summary. And I would just, so in photoionization modeling, we make simple assumptions that the things are time independent, that we have some density which we can solve for, and that the geometry and the dynamics are very, very simple. We obviously are interested in more complicated science goals. We'd like to understand what the geometry is. We'd like to understand what the dynamics is. We'd like to learn the abundances, and we'd like to look for relativistic effects or, you know, unseen sources of energy. And all of these things necessitate some care in order to avoid inconsistencies and to get the most out of our models that we can. And that's it. Thank you.
All right. Thank you very much. So we do have about 4 minutes for some questions. We have one question from Slack, which has also been posted in the chat panel by Leah. The question is from Kishale. The question is it optional or mandatory to modify the default metal abundances used in XStar from 1989 when analyzing more recent data? For instance, the tables of Wilms et al. 2000, which is the default suggested for AGN, or the more recent ones such as Lauders and Asplund.
Well, it's not mandatory. It's always optional. I will point out that if you use WarMabs or Photomis, the analytic models, those can use the abund command inside of XSpec, and so you can easily switch abundances using that command. It just loads the whole array of abundances in for you. So that's quite easy to do.
Okay. So let's see. We have a so Randall has posted something, a question. Time-dependent PI could help tell us photoionization. Time-dependent photoionization could help tell us the mass of warm absorbers if the central AGN varies. So is there any way to use XStar to simulate this time-dependent photoionization?
Well, I don't think, not in a particularly useful way. We can get, certainly we can test, we can get the, you know, you can look at a rate and tell you, so then you can infer the time scale for that would be associated with that process if the flux were to change, for example, or the density. To actually make a quantitative calculation, that's something that's actually being worked on right now. I mean, I know that other people have done this. Yella has written a paper on this, I think, and so this is a very worthwhile thing to be looking at, and I'm aware of it.
Okay, so Nicholas Gorgon has a question. How long would one expect highly asymmetric structures to exist?
I guess I'm not in dynamically, or
probably this might be related to Randall's question about the time dependence of warm absorbers in the central AGN. So for example, with non-spherical geometry.
I mean, that's a question about the dynamics. I mean, obviously the thermal time scale matters for that as well. If the gas is condensing and turning into filaments or being heated and ionized, those things matter. I mean, certainly I can tell you from my own estimates that for warm absorbers, the time scales are not very long. So certainly they're reasonable. You know, if the stuff is at a parsec, I think a reasonable time scale is a week or so. You know, so it's not that long. It's long enough to be able to be seen.